Chapter 4, Exponential and Logarithmic Functions, Section 4.4, Exponential and Logarithmic Equations. We're now going to take some of the concepts and methods from the earlier sections of Chapter 4 and apply them to solving certain types of equations. So we'll begin with exponential equations. And an exponential equation is basically an equation where the variable is in the exponent. And we'll see that exponential equations arise in the solution of various applied types of problems involving exponential growth and decay. So an equation that contains expressions of the form a to the x is called an exponential equation. If both sides of the equation can be expressed as powers of the same base, then a solution can be found by equating exponents. So in some cases, you might have more than one exponential expression within an equation, but all of those exponential expressions can be expressed in terms of the same base. If we look at example 1, we want to determine the value of x such that 9 to the x plus 1 equals 27 to the x. So notice that the variable occurs in the exponent. Notice also that 9 and 27, while not the same base, can both be expressed in terms of a base of 3. 9 is 3 to the second, 27 is 3 to the third. So if we write 9 as 3 squared, then that's raised to the x plus 1. And 27 as 3 cubed, that's raised to the x. Then we can express both sides of the equation as powers of 3. Now by properties of exponents, we can multiply the exponents on the left-hand side, writing this as 3 to the 2 times x plus 1. And similarly on the right-hand side, 3 to the 3 times x. So we can multiply the exponents. Then, since the bases are the same, we can equate the exponents. So it would follow that the exponents would have to be equal. That means we can drop the base of 3 altogether, and we obtain the equation 2 times x plus 1 equals 3x. This is just a basic linear equation, and we just solve it as we normally would. We can distribute the 2 on the left. Then we can subtract 3x from both sides. That give us minus 1x or minus x on the left, and subtract 2 from both sides. That would give us negative 2 on the right, and then divide both sides by negative 1, obtaining x equals positive 2. So the solution to the equation would be x equals 2. Essentially, this would be telling us that 9 to the 2 plus 1, or 9 to the third power, has the same value as 27 to the second power. Now, if both sides of an exponential equation cannot be expressed as powers of the same base, which is actually more common, we may solve the equation using logarithms. Usually either common logarithms or natural logs are used. That's due to the fact that we can use a calculator for such logs. For common logs, that is base 10, or for natural logs, that is base e. We can use the calculator functions that are available on any scientific calculator. So those types of logarithms usually are used along with the power rule. The power rule allows us to bring exponents out of a logarithm in front of the logarithm, as I'll be demonstrating. But logarithms of other bases may also sometimes be used along with the change of base formula. So There's more than one approach you can sometimes take, but I'm going to usually use, if I can, I like to use natural logarithms. So usually I'll be using natural logs. Let's look at example 2, part A. 5 times 2 to the x minus 3 equals 17. One of the things we want to try to do, if necessary, is isolate the exponential part of the equation. Now, in this case, the exponential part is 2 to the x minus 3. So we want to get that by itself on the left. That means we should divide both sides by 5. One thing you do not want to do here, you do not want to multiply the 5 and the 2 and write 10 to the x minus 3. The 5 and the 2 cannot be multiplied together because the bases are, well, you know, if the bases were the same, we might be able to combine. But if you have two different base expressions, 5 and 2, you cannot combine them in that fashion. You're basically violating the order of operations if you do that. So we're going to divide both sides by 5 and write this as 2 to the x minus 3 equals 17 over 5. Now, since 17 fifths, which is 3 and 2 fifths, can be written as in exact form as a decimal, I'm going to do just that. It will just make it easier to write our solution. So I'm going to write this as it's 3 and 2 fifths, so that's 3.4. Exactly 3.4. If I would have obtained a repeating decimal or something like that, then I would have left it as a fraction. But here it's more convenient just to work with the decimal form since it is in an exact form. All right, now the next step is the key step, and that is we'll take the natural log of both sides of the equation. That is, we substitute both sides, since they are equal, into a natural logarithm. Now, I could use a base 10 logarithm, log, if I preferred. You can use either type. Then the power rule, which was mentioned up above here, that would mean that we bring the exponent to the front of the logarithm. This rule was used in the previous section, 4.3. We introduced the power rule along with the product and quotient rules. All of these rules can be used to manipulate logarithmic expressions, writing them in different forms. And then on the right, still ln of 3.4. I don't need the parentheses there. Now, there are two things I could do at this point. I could distribute ln2 to remove the parentheses on the left, or what actually is a little bit simpler in this case, we can divide both sides by ln of 2. ln of 2 and ln of 3.4 are both constants. They're just irrational numbers, so we can just treat them as just ordinary constants. We can divide both sides by ln of 2. That would give us, on the left, x minus 3, and on the right, ln 3.4 divided by ln of 2. That cannot be simplified. You just have to leave it in that form. And then add 3 to both sides. Making sure we add it to the outside of the fraction. ln 3.4 over ln 2 plus 3. Then we can use a scientific calculator to approximate this. You should verify that to the hundredths place, that approximates to 4.77. So if x is about 4.77, then the exponential expression 5 times 2 to the x minus 3 will be approximately 17. Let's now look at the equation in example 2, part B. This one's a little bit more challenging, but it's of a similar type. There's no need to isolate any of the exponential parts because they're basically already isolated. We have two different exponential expressions here. two different bases that are not compatible. So we'll just immediately take the natural log of both sides here. Natural log of 3 to the 2x equals natural log of 5 to the x minus 1. Let's use the power rule now. Bring the 2x down and bring the x minus 1 down. You see how I put the x minus 1 in parentheses on the right hand side. So really the main use of logarithms here is to get the variable out of the exponent so that we can solve for it. Now in this case, because there's an x on both sides of the equation, I'm going to remove parentheses on the right using the distributive property. So I'm going to write 2x ln 3 and then x ln 5 minus 1 ln 5. That's just minus ln 5. So that removes the parentheses from the right. Then what I need to do is get the terms containing x on the same side of the equation. So I'm going to subtract x ln 5 from both sides. So I have 2x ln 3, then minus x ln 5. And then on the right I have just minus ln 5 left. Now the terms on the left, in one sense they're like terms because they both contain x to the first, but because the logarithms are different, we can't really subtract the second term from the first. So the better thing to do here, really the only thing we can do, is factor out x from both terms, leaving us with 2 ln 3 minus ln 5 in parentheses. And then still minus ln 5 on the right. Then we can divide both sides by 2 ln 3 minus ln 5 to solve for x. So we have in the numerator minus ln 5, in the denominator 2 ln 3 minus ln 5. That would be considered the exact form of the solution. And I would like you to always attempt to obtain exact solutions of equations before you use your calculator to approximate them, and then to approximate everything on your calculator in one step. So if we do that for this expression, we should obtain the following approximate solution of negative 2.74. Now, what you're going to have to do, although you don't have to write these in, when you use your calculator, you'll have to make sure that you enclose the difference in the denominator in parentheses. Otherwise, you will not obtain the right result. You have to make sure that you divide by that entire difference. So you have to insert parentheses when you enter this in your calculator, or it will not give you the correct result. So try to obtain an exact solution before approximating. Do not approximate, say, at this step right here. Do not approximate ln of 3 and ln of 5 until you have completely solved for x. Because the best you can do at that point is obtain an approximate solution. And there's really no need to do that until you've solved for x. Try to obtain an exact solution. You will be expected to do that on the next test. We'll continue with these notes in the next video.